Okay, all right, let's get started. Happy Monday, everybody. Any questions before we dive in about the programming assignment, quizzes, readings, anything like that that you want to talk about before we get started? Everybody pretty happy? Anyone notice the bug on the quiz? I mean, a couple people did because they posted on Piazza. Yeah, there was a mistake on the quiz. I was hoping someone would ask in class. There was a mistake on the quiz. The one where the number had just, I'm going to post on Piazza. I'm not going to try and explain the whole example in class. I'll just post on Piazza so people know. I changed it so you'll get credit because the right answer wasn't there. It was just a copy-paste bug on our part. But the one that was asking, what number does this represent? And it was like 0x8 and then a bunch of zeros and then 1, 1 at the end. We copy-pasted the wrong example, and that's actually a large negative number. It's not -8 or any of the things that were there. So we'll post on Piazza to clarify it. It was a total mistake on our part. If you posted late yesterday, if you submitted late yesterday, we had fixed the question, and you'd get a little message that said, no, the right answer was this. It wasn't what you picked. Sorry, but we'll post on Piazza about it. So there was a bug on the quiz. So I don't want to leave that misconception floating around. So be ready to see on Piazza. We'll announce that fix. Okay. All right. How many of you have started PA2? Nice. Oh wow, awesome. Good job, everyone. Okay, cool. All right. So we left off on Friday, we sort of went through the initial stages of doing some of this tag-based representation for values. We sort of stopped when we were going to call an error function. I said there's going to be a little bit of a hack in programming assignment 2 for you to call the error function. We'll come back to talking about calling functions next week. So what I want to do today, so today and Wednesday we'll really be talking about sort of the mechanics of calling conventions so that we can get functions into our language, because the next feature we're going to add to the language is the ability to define and then call functions. Something you kind of need if you want to have a language that feels at all realistic. And so what I'm going to do today is introduce a very simple calling convention that we could try. It's not a terrible idea, actually. The calling convention is okay. I've actually used it I actually used this calling convention or something very close to it when I taught this course last year. But I want to point out a problem with it, because I think it's a really interesting problem. It's not like something is incorrect about the code that it generates, but it's a sort of interesting interaction with other tools that happens when you use this calling convention. And so I want to talk about that and then talk about a solution for it, have you sort of come up with what we need for a solution for it. So keep in mind that when I talk about the calling convention I'm going to describe in a minute, imagine what the possible problem could be with this thing that I'm describing. Okay? So I'm going to use some slides for this because I just have something that I want to communicate to you. So I'm going to sort of use slides for a little bit, and there's some embedded questions here. Okay. So this is going to be the syntax for function definitions in our language. And the way we're going to set up the next programming assignment is, instead of the program just being like one expression, the program is going to be a sequence of function definitions. Okay? So instead of just being one expression, it'll be a sequence of function definitions. Pay no attention to the trailing colon. There we go. Perfect. It'll be a sequence of function definitions. And function definitions are going to be written as open paren def, and then in parentheses we have the name of the function and the name of its argument, and then the body is a single expression. We're going to have one function definition called main, and that's going to be where we start evaluating. And main is going to take, much as you've gotten used to from PA2, input as an argument. Right? So this is like having a main method that takes the command line arguments. Right? And the evaluation is going to start in main. Okay. So there's a couple different pieces of this concrete syntax. There's a place where the function name is defined. That's g, f, and main in this example. Okay. There are argument names. Right? So here's input x and y are the argument names here. Here's the function body. These are the expressions that actually evaluate when we call the function. Here are function names appearing in positions where we call them. Function names appearing in positions where we call them. And finally, we have expressions that are going to be the actual argument values that are passed in. So these purple expressions are arguments that will be evaluated and then passed to the g function or passed to the f function in this example. Okay. This is like pieces of concrete syntax. This looks kind of like Python, but with parentheses. Python uses a def keyword for its functions. I'm just going to do one argument functions in class, much like I did one argument functions for one single let bindings in class. And then part of the PA will be generalizing to a list. But I'm just going to talk about one argument in class. And so there's a couple ways we could try to represent this, right? I've highlighted all these pieces of syntax here, right? And these ought to somehow show up in our definition of concrete syntax and our definition of abstract syntax, right? One of the first things we're gonna have to do is get these S expressions and turn them into abstract syntax so that we can compile them, right? That's what's gotta happen here for us to make progress. I want to show you two potential options, right? One option is, and so I've sort of color-coded the abstract syntax based on what I highlighted above. One option is, well, everything we've done so far is under this expression data type, so why not have a new E definition kind of expression and a new E application kind of expression? So E definition is going to have the name as the first string, the argument name is the second string, and then the body. And then when we do an application of a function, we'll have the name of it and then the argument expression. Another choice is that we could have just applications as a new kind of expression, and then definitions are some kind of special thing, and then there's some type for what programs are. Maybe they're a list of definitions and then some expression for main, or maybe they're just a list of definitions. So I want you to talk about this a little bit. Which representation do you want to try first? Which one of these representation makes the most sense to try first? Think about what the consequences of picking one of these representations might be. Like, what do you think the consequences are? Talk about this for a minute or two, because this is really when you add a new feature to a language, if you're maintaining a language and you want to add a new feature, you're going to have to make decisions like this all the time, right? I want to add this new thing. Where does it go? What kind of abstract syntax is it? So talk about this for a minute. Which of these representations do you want to use? Okay. So so first of all, any questions that came up while you were talking about this, about what's on the slide or anything like that? Any questions that came up? Questions first, and then we'll take some suggestions for why people wanted one over the other. Questions? Questions? So at least like one weird thing on the slide. No one was saying like, oh, what's going on with this thing on the slide? Huh? Yeah. EAP? What's weird about it? What's weird about it? So it means application or something like that? It means using a function, because our EAPs are going to correspond to like using F and using G with an argument. Yeah. Other things about the slide. Other things about the slide. Yeah. Mm-hmm. So there's on the left-hand side, the first expression in this EAP on the left-hand side is also an expression, right? Like, well, how do you call an expression? I know how to call a function with a name. How do you call an expression? What the heck does that mean? Right? Okay. Other things about this slide. Other things about this slide. There's a lot to talk about here, actually. Other things about this. Other questions you had? Yeah. Mm-hmm. You're saying eventually we very much want this and this, these two spots where I have string in red here that correspond to argument names, to be string list, right? Because we don't want to only have functions of one argument. Yeah, so in class I'm going to stick to functions of one argument just to keep things simple, so I can sort of fit examples on the screen and things like that. In the PA it'll generalize to a list. And much like let generalized from a single binding in class to multiple bindings in the PA, it's sort of going to be one of the things you figure out in the PA. That's a really good point, though. Just with this representation, we'd be sort of slow, or sort of short of where we'd want to be for expressiveness in terms of functions. Yeah? Why is there a prog on the right side but not on the left side? Yeah, so that's a really good question. Does anyone want to answer that question? Why is there a prog on the right side but not on the left side? Why is there a prog on the right side but not on the left side? Could be an explanation for that. Yeah. Ooh, interesting. So you're saying maybe the way this is set up is sort of like let, where we have like let and a value, and then there's the body, and then there might be more lets with a value and then the body. And so we can just use a bunch of lets to get the behavior of having an entire sequence of definitions followed by a body. And here, that's not what's going on. Here, that's not what's going on, because since def isn't an expression, we couldn't use it inside the binding of a let. It's actually an important point about this. If we make def be a different type than expression, right? This is definitely not an expression because it's not underneath type expr. We couldn't use it in a let. We wouldn't be able to use it in let x equals some definition because it just wouldn't fit in the type, right? We're saying we want this to be a distinct thing from expressions. These definitions are their own thing at the top level. They're not expressions. That's a pretty interesting distinction between these two. If def is an expression, it means we need to answer all sorts of questions about it. Like, what does def evaluate to? Like, right, plus evaluates to something, like a number, right? We take the two expressions and add them together and get a number. What does a function definition evaluate to? What does a function definition evaluate to? My gosh. Monday morning, Joe. Have you ever seen a language where a function definition evaluates to something? Have you ever seen that happen? Yeah. In some languages, it evaluates to a function value, right? There's this idea of a function value that you can pass around. It's a value like a number or a list. You can pass functions into other functions, right? So this interpretation on the left is saying definitions are a kind of expression. We could evaluate them, store them in variables, pass them around, try and add them to each other, which hopefully produces an error, right? But that's what this left-hand representation is saying. Definitions are just like any other expression, and somehow we'll figure out how to give meaning to function values. That's what that left-hand side is saying. The right-hand side is saying, well, let's take a more sort of like C interpretation of this, where you can't just stick a function anywhere. You can write functions at the top level of a C file, right? You can't just go writing functions in the middle of an if statement or in a local variable. You have to write all the functions at the top level. And then when we call functions, we'll just refer to them by name. There's not going to be any business of passing them around. I know there's function pointers in C, but set that aside for a minute if you're thinking about that. And just think about it as there's top-level functions, and we'll call them with their name. Okay? So that's the difference between these two representations. The one on the left says, well, if we're going to take this approach, we better know what functions evaluate to. What value do you get when you evaluate a function on its own, right, without applying it? And that's a really interesting question. That's not a question we're going to tackle now. So this week, and for PA3, we're going to take this approach. All the functions are going to be top-level functions, right? So we just have top-level function definitions, and then we can call them using their name. Later in the course, after we talk a little bit more about how to interact with heap-allocated values and get through a little bit more material about memory, we'll come back to this representation and talk about how we would handle it. And this really has to do The vocabulary word for the left-hand side, the thing we need if we want to do a good job at this, is that we would need to implement closures, which is something you might have heard about. Depending on which version of 130 you took, you might have heard a lot about this vocabulary word of closures. And so we'll come back to that later. But I want to emphasize that we're making this decision for now that functions are going to be these top-level entities. We're just going to have a list of function definitions, and then we're going to call the main, main to get started. Okay? Any other questions about what's on this slide? Questions about this? Okay, cool. So let's, if we take this as our representation, now one of the things that's going to happen if we pick this as our representation is we're now not just going to have compile expr, right? Before we just had compile expr, right? That was the only compile function we had aside from the parser, right? We'd parse it and then we'd just compile expr. Now we need to compile definitions, which is a new kind of thing that needs to happen. We have to know how to compile a function definition, and we're going to have to compile a whole program, right? This program, which is this list of function definitions. So there's sort of more structure in what we'll need to do in the compiler for what kind of code is going to come out. And the new case in compile expr is going to be this app case, right? That's sort of the new expression we have to handle, is how do we compile a call to a function with a particular argument. Okay. And so the things I want to talk about today, the thing I'm going to go through in some detail today in specific examples, well, one particular specific example, is the instructions that we'll do for a function call, and then the instructions that we need for the function's definition or for the function's body. And these two things correspond to the two sides of a function call in things you've seen before. Like in cse130, you talked in detail about C's calling convention, right? Where there were things that the caller was responsible for and things that the callee are responsible for. And that's where we're going to start making our own design decisions. But here's something really important. There's nothing about C's calling convention that is like a fundamental truth of the universe. Okay? It's true. There is nothing about that calling convention, depending on if you did Spark or ARM or whatever architecture you learned in cse130 or whatever prerequisite you took for sort of learning about assembly. There's nothing that's like fundamental, like given to us from on high about that being the one true calling convention in the world. We are completely free as compiler designers and language designers to make up any strategy that satisfies what we need for what happens on the caller side and what happens on the callee side. As long as it acts like a function call for the programmers in our language, right, and they're happy, right, we can make design decisions here. We don't have to do what C does. So to emphasize this point, I'm going to introduce a calling convention that isn't exactly C's. It's a little bit different from C's, but it matches the way we've been thinking about using the stack and using ESP, the stack pointer, and sort of using these addresses that are subtracted from ESP. So I want to introduce an idea. I kind of like doing this because it emphasizes what makes a calling convention rather than just like doing C's calling convention again. So we'll go through an example and then we'll see one way we could improve it. Okay? All right. I'm just assuming sort of single let binding, so I'm keeping the language fairly simple for the examples that I do in class. So on the left-hand side, at the top, I have this little, think of this as like the main expression. This is what's going to start evaluating. So it's this let of x to 10, let of z to a call to g, and then adding 3 to the result of that. And then on the right, g is just a function that adds 1 to its argument. Okay? So we're going to talk about the instructions generated for the caller, right? There's definitely an app expression up here where we call g over on the top left. And then we'll talk about what instructions we need for this function body. We're going to talk about sort of what needs to be remembered and what needs to be passed around. And to start out, I'm just going to say ESP contains the value hex 34, and hex 34 is some unknown, holds some unknown value. This is like below the space that our program is using, right? So our programs in like PA2 and PA1 and PA2 are starting at ESP minus 4. That's where we're going to start using space. Okay? And ESP is starting looking at that unused space below there. Okay. So I'm also, just as a note, I'm not going to tag all the values in these examples in class. I'm just going to, numbers are just going to be numbers. So 10 is the representation is going to be 10. the tagging stuff isn't particularly interesting for these examples and just adds more instructions. So I'm not using fancy representations here. Okay? So the first thing that's going to happen is we're going to move 10 into EAX. This is processing the top let on the left. Right? We always have to get the value of the let binding into EAX. And so that changes EAX to be 10. Then we're going to take that value, and because it's a let, right, we're going to store it on the stack. So 10 is going to get stored on the stack, and that's stored there because we're doing a let binding. Right? So that's just processing the code for let x10. And so now we get into the code for doing this function application, because the next thing that needs to happen is we need to process calling g. Okay? So here's how we're going to do this. We're going to get the argument value, which in this case is, what's the argument value for this call to g? What's the argument value? What's the argument value for this call to g? Right here. Argument value for this call to g. Talk about it for a minute. Come up with what is the argument value for this call to g? What do I mean by that? What the heck do I mean by that? There's this call to g here. What's the argument value to it? Talk about it for a minute. Okay, so there might even be a few different ways you want to answer this question. So first of all, any questions or confusions that came up trying to talk about this? Questions or confusions that came up in response to this? I saw some quizzical looks when I was looking around, so. Questions? Everyone resolved their questions by talking to each other. Yes? So g is a function, yeah. G is the name of a function defined up there by this def for g that's going to take in y. Yeah, so what's the argument value? What's the argument value going into g then? X, so x is the expression and the value that it's holding is 10, right? So the reason we're moving ESP minus 4 into EAX is because we're trying to get the value for x into EAX, right? That's the answer for that x expression, okay? So that's going to be the first step of calling. We need to get the values for the argument, right? Or the value for the argument, right? If we had multiple arguments, we'd need to get all of them somehow. But with just one, we'll move it into EAX. And then we're going to start the work of doing the call. So I'm going to introduce a label here called after call. After call. So there's going to be another label down here, after call. This is going to be where evaluation proceeds to when we're done with the function call. So we're going to do some work here to set up arguments and things like that and make sure we jump over to G to start evaluating the instructions in G. And this is where we want to come back to once that function call is done. So some instructions will happen here in this part to set up the call. Then we'll jump over here, do some work for the body of G, and then we ought to come back and start evaluating it after call when that's done. So I'm making the label here explicit. Sometimes you'll use call and ret instructions and things like that. If you saw C's calling convention, I'm making it really explicit. That's the label we should jump back to when we're done with this call. Okay? And I'm moving after call into ESP minus 8. I'm moving the value of a label into ESP minus 8. So ESP minus 8 is this spot. This is, I'm just going to write it as the label. This would actually be some value that corresponds to an instruction stored there. Anyone know like the vocabulary word we'd use to talk about what that value is? What's it called? What's it called? What's this spot on the stack called? This spot for this label of an instruction we come back to after a function call. Return address, that's the return address. Right? So I'm explicitly moving the return address into the memory with move. I'm saying that label, wherever that instruction is, I'm storing that to the stack explicitly. Okay? Now, I'm going to next store the current value of ESP. So right now, ESP, remember, I haven't changed ESP at all. It's still pointing at this 34 value. So I'm going to remember where ESP was. And this is something that often happens in C's calling convention is we're going to need to keep track of where the stack pointer was before we did the function call so we can move it back there after we're done with the function call, right? So I'm going to store the old value of ESP onto the stack. So that's that hex 34 value. That's where the stack pointer was initially. So we'll be able to look that up later and restore the stack pointer to where it was before we did the function call. And then I'm going to move EAX into ESP minus 16. What does this correspond to, do you think? Describe a little bit what this is doing? Yeah. It's passing the argument. Yeah, it's passing the parameter. So EAX is currently holding the value of the argument, and that's going to be moved onto the stack as well. So these three words at 2C, 2.8, and 2.4 are the return address, the old stack pointer, and the argument. So this looks like a calling convention, right? I've got the information, both the argument that this function needs and then the information we need to come back to the state that we're in right now. Okay? And I just used relative addressing from ESP to do this. Okay? Now I'm going to subtract 8 from ESP. Subtract 8 from ESP. This is going to be, actually, this is a good question to ask. Why am I subtracting 8? Like, why 8 from ESP right here? Reason to subtract 8 from ESP? Why 8? Why 8? Who cares about 8? Yeah. For two words. Where's ESP going to point after this? 0x34? Well, if I subtract 8 and it's at 34 now, it'll be at 2C afterwards. So this is going to change ESP to point to 2C. So now ESP is pointing at the return address. It's sort of like these three words correspond to the information that function needs for its call. And now we're making ESP point at the bottom of that, right? So this is like starting the stack frame for this call to G. Now ESP is pointing at the bottom word in the stack frame. Okay? So it's pointing at the return address. And then we'll jump over to G. So then we're going to jump to the label G, and we'll make the label G have whatever code it needs to have in order to add 1 to the argument and return it. So let's talk about G. So one question here is, from G's point of view, where is the argument y in terms of the current value of ESP? If we think about the argument, where's the argument y relative to ESP? Where's that? Let me, oops. 5, 4, 3, 2, 1. Okay. Okay. All right. I'll talk about this for a sec. Make sure we're all on the same page. Okay, click in again. Okay. 5, 4, 3, 2, 1. Okay. All right, yeah, so right now, right, the value in ESP is hex 2c. So ESP is sort of pointing at this spot with a return address. And from G's point of view, it can rely on the fact that 2 words above this in the stack picture, so -8, is where the value of its argument is. Right? So its argument y is guaranteed, based on how we set this part up, that there's going to be the return address, then the old value of ESP, and then we'll have the argument. So this is going to be at ESP -8 from the point of view of evaluating G. It's going to be C. Okay, let's jump forward a little bit here. So that tells us that if we want to get the value of the argument anywhere in the body of G, we can get it at ESP -8, right? So if this is get the value of y, right, that's going to go fetch the value of y and put it in EAX. What does that mean for the environment when we compile the body of this function? What does that mean for the environment when we compile the body of this function? Yeah. So if we're going to have like let bindings or other calls to other functions in here, right? If we want to use more stack space in here, we shouldn't start at ESP -4 because we'll start overwriting stuff we care about. So the stack index had better start us at least ESP -12 because we know that the space up to ESP -8 is used. Yeah. What else? What does that tell us about compiling the body of this definition? What do you think the environment should be for the call to the body? What should the environment be? What should the environment be? I'm looking for someone else. What should the environment be? Yeah. So the type of the environment is this mapping from the names to their stack location, to their stack index, right? And we're going to compile the body of G, which is this +y1 expression, with some environment, right? We've got to have an environment when we compile these expressions because we need to know what to do with any IDs we find. So what does that mean for the environment we should use for compiling the body of G, right? If the environment means mapping from names to stack indexes, what environment do we want? We agreed that the stack index probably should start at like 3, right? So we don't use ESP -8 again. But what about the environment? The environment. Yeah. So do we need to should we be able to use x and z in the body of G? Ooh, that's an interesting question. If I wrote like x plus x1 in the body of G, do you expect that to work? Oops. Thanks, Apple. So you're saying, well, the environment for a function shouldn't contain any let bindings from other places. It should only contain sort of the global functions. Anything other than the global functions? Anything other than the global functions? Anything else? The parameters, so y. So that means inside G, right, the environment somehow we should be able to call functions, right? But also, we need to know where to find y relative to the current value of ESP, which means we need an environment that says y is at, well, if we take our current interpretation, so ESP -8, y ought to be the stack index 2. Right? So at the start of compiling this function body, we ought to say the environment is y has stack index 2. So anytime we see an EID y, we turn it into ESP minus 8. Right? We look for it in the right spot. So that says something important about when we compile a function definition, what the environment looks like to find the parameters. Because this function is going to rely on the fact that we've set things up so the argument is 2 away from where ESP currently is. So next, I'm just doing add 1 to this, right? So I'm just sort of simplifying what what plus does, right? So we'll add 1 to this. And then we have the answer for this function. Oh, go ahead.
So in our language that we create, do we want G to be able to access X?
So let me ask it this way. If let's imagine this as being like in the body of main, right? Like we wrote int x equals 10 in main, int z equals g called on x. In that case, do you want the function g to be able to access those declarations? If I write int x in one function, in another function, can I access that declaration? By using its name? Okay, all right. I'm going to ask this very explicitly. Okay. 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 5, 4, 3, 2, 1. Okay. All right. So in this example, right, people are asking, should G be able to see like X and Z? By intuition from other languages, I think not, right? Like we should not have functions like yanking things out of each other's scopes. Right? Each function just knows about its parameters and any local definitions. Is that a satisfying answer? Okay. Yeah. Here or here? Ah, this 8? Yeah, why is this 8? Why not 16? Why not 12? Yeah, what could that possibly be related to based on, I'll say it's based on where the application appears in this expression. What does that have to do with? Yeah. So one option is because there's only one parameter? Yeah. The new stack pointer had better match the return address, so wherever the return address goes. How do we figure out where the return address went? It's related to the stack we used in the context that's making the call. So actually there's these two main options. One is it has something to do with the number of arguments, and the other is that it has something to do with the context of the call, right? We need to make space based on the context of the call. So the way to think about this is everything below this where we put the return address is local space we're using for the let bindings, like the let binding for X and stuff in the current context. So we need to move the stack pointer up past the current context, right? Basically, the current stack index. So this 8 came from the fact that this call to G is sort of 1 deep in the stack index nesting, right? So here, we needed to make space to store X. If we use X after this, we don't want to like overwrite that space. So we need to move ESP up past that, and that's where the return pointer is going to be. If there were more let bindings before this call, we'd have more intermediate values we're storing, and so this would be a larger subtraction. Right? So if we had let x equals 10, let y equals 20, let a equals 12, right? We'd start subtracting 12 and then 16 and so on from ESP because we need to make room so that we don't start overwriting the space we have for local variables with this return address? Yeah, it's a really good question. Okay, so we're going to add, and then we're going to, so that puts 11 in EAX. And then I'm going to use an instruction called ret. And what ret does is it assumes that ESP is currently pointing at some address of an instruction. And it subtracts 4 from ESP and jumps to that instruction. That's what ret does. This is pretty typical. Most architectures have something like ret that expects the current stack pointer to be pointing at a return address, jumps there, and does some manipulation with the stack pointer. Okay? So since we're at 2C for ESP, that's a return address. Ret is going to subtract from ESP4, and then it's going to jump to whatever instruction was there. So this is now using this stored return address to come back to after call. Okay? So now we're at after call. ESP is kind of an odd value. It's hex 30, which is a little odd. That wasn't any of the values it had before. But we do have the answer for calling the function in EAX. That's pretty good, right? The goal of the function application should be to get the answer for the function call into EAX. So 11's in EAX. That seems promising. So now we're going to process whatever needs to happen after the call. The first thing we're going to do is we know that right now ESP minus 8 is holding the old value of ESP. That hex 34 is what we stored there before we made the call for the value of ESP. We stored it so we could restore it later. So we're going to restore ESP to what it was before. Just quick to make sure we're on the same page. What's the current value in ESP minus 8? Five, 4, 3, 2, 1. Okay, talk about this, because the answer is on the screen. You can interpret what's on the screen to get this. So talk about this for a second. I'm going to leave this open for about 30 seconds for you to click in again. Yeah. Why ret does that? I mean, the why is like the inexorable weight of decades of history of x86, right? I mean, so that's kind of the why. We could use a combination of instructions to like grab the value at ESP and then jump to it, but ret sort of does that work for us. And in the C calling convention, ret sort of nicely matches up with some stuff, so that's why it's done. Yep. Yeah, so ret does this extra piece of work. Really the thing that's nice about ret is it uses the current value of ESP as an address to jump to. Yep, then it adds the 4. Yep. Yeah, I mean, it's just, that's what ret does, right? So, yeah, I mean, you can imagine that the different ways you set up calling conventions, that's very nicely what you want, or you have to do some patching up afterwards. Okay. All right, so I'm going to close this. Okay, yeah, so what's at ESP minus 8 right now? ESP is containing hex 30, so the value in ESP minus 8 is hex 34. So this is going to change things so that we have hex 34 in ESP. This is nice, because now any references we make to variables like x and z that are in the context of that left-hand expression now are making those references relative to what the value of ESP was when that expression was evaluating. Right? We're not using this updated value for this function call. We've restored things. Okay? So we're going to take the EAX, which currently holds 11, which is the answer for calling this function. Now we're going to store that at ESP minus 8, which corresponds to the variable z, right? So we're storing things now in the context of these lets. So x had stored 10. Now we're going to store the answer. That's the variable z. So we start reusing the space for this function call. We don't need the space for this function call anymore. We're done. And then we can sort of process this arithmetic. So like move 3 into EAX and add to it if we need to. Okay. Oops. There. And move 3 into EAX and add to it. And that gets us our final answer. Okay. So there were a couple of things that happened here that were, so we get 14 as our final answer. So there are a couple of things that happened here that are kind of interesting. If we think about this from the point of view of the caller with one argument is always going to put this after call label onto the stack first, above the current stack index. Then it's going to store the current value of ESP. Then it's going to store the argument. Right? And so we're always subtracting the point ESP right at that return address. And we're always starting this at the current stack index because that's where we have space to create this stack frame. From the point of view of the callee, the first argument is always going to be an ESP minus 8. So the environment should always be, well, whatever the parameter is, and then 2, so that we get minus 8. We start at this higher stack index for any local variables, and we expect the value in ESP when the function starts to contain a return pointer. And we can use ret for that. And then after the call, we rely on the old ESP being at ESP minus 8 and expect the answer to be an EAX. Yeah? Yeah, so sometimes the call, in C, the callee is responsible for putting this back. In this calling convention, the caller is responsible for putting it back. That's the way to think about it, is that the caller has a little bit more responsibility. In C, at the end of the function, you'd see something about it putting ESP back to where it was. Yeah? Interesting. Do we really need to save it? That's a really good question. I'm going to not answer it right now because I want to get to this one other issue. Yeah. What is the point of storing after call onto the stack? What is the point of storing? So you're saying why not just jump to after call in G? We might call G from many different places in the program. So G can't assume that it's going to jump back to only one return address. Right? Every place that calls G always jumps to G. But when a function is done, it may jump back to one of many places in the program because it could be called from many places. So we have to store where we're going to return to somewhere. Right? Because for different calls to G, that value will be different. And it jumps there. Yep. Yep. Okay. Cool. I have 2 minutes left. That just died. Nice. I almost asked someone for a charger, but I thought I had just barely enough. So I want to bring up one issue. I'm just going to use the chalkboard for this last issue. And this is the thing that I want to point out is a problem with this. Okay. So I just have one picture I want to draw. Right? So when we do something like right, we get an instruction like move into ESP minus 4 the value of the value EAX. Yeah, we get something like this. And before that, we moved into EAX the value 4. If you take this, assemble it, compile it in the way we have done in this class, and then run an old friend, Valgrind on it, Valgrind with memcheck on is going to say, whoa, you can't write to memory that's subtracted from ESP. That's not on the stack. Because Valgrind thinks that it's analyzing C programs. And C programs don't ever write to addresses above ESP. C programs always have this structure. They always have this structure where they have a base pointer pointing at the bottom of their stack frame and a stack pointer pointing at the top of their stack frame. Right? This is always the structure during the evaluation of a program that was compiled by GCC. Right? This is just always what's happening. And Valgrind makes sure that all of the writes are in this region for local variables for the function. If you start writing up here, Valgrind says you might be using like pointer arithmetic incorrectly or doing something wrong. So you get tons of Valgrind errors if you run our binaries right now. We have this